Our next speaker will be Quinn Minnich from Michigan State University, who will be talking about a proof for enumerating admissible pinnacle sets. And just a quick reminder, please stay muted the entirety of the talk and wait until the last 5 minutes to ask questions. Thank you.
All right, I want to thank you very much for coming to my talk and me speak here today. What I'll be talking on is some joint work that I did with Dr. Bruce Sagan and Jingting, Rachel, Jamie, and Alex. We worked on a lot of results for pinnacle sets, so this is going to be one of them that I'm presenting. So before we get started, we should probably talk about what pinnacle sets are. If you have a permutation of the numbers 1 through n, then a pinnacle value is simply any value of that permutation which is larger than the values on either side of it. And if you take all such values together, that gives you the pinnacle set. So to make it concrete, let's do an example. Suppose we have this permutation. To find the pinnacle values, we look for all the values which are larger than the values surrounding them. And in this case, the 9 and the 8 are those values. And then that's the pinnacle set. Note that 6 is not included, even though it's larger than the 5. A number on the end of a permutation can never be a pinnacle because there's no number on the other side of it to make it to be smaller. Now, if any of you have dealt with permutations much in the past, you may be thinking this is kind of similar to something called a peak set. And it is similar, although there is a difference. For those of you who have not heard of it, the peak set of a permutation is all the indices where an element is larger than the elements on either side of it. So pinnacles are the values, and then the peaks are the indices of those values. I'm not going to talk about peaks in the rest of the presentation, so you don't need to worry about them. But if you're curious the connection, that's what the connection is. So given a permutation, you could find the pinnacle values without too much trouble. It's worth asking, can we go backwards? If you take a subset of the numbers 1 through n, is it possible to find a permutation that has those numbers as the pinnacle values? And if it is possible, then we say that set is an admissible pinnacle set, and otherwise it's not admissible. So again, an example is worth 1,000 words. So is the set 3, 6, 9 admissible? Can we find a permutation that has these 3 numbers as the pinnacles? And yes, we can. Here's an example. Notice I say an example because there's more than one permutation that will work. We could swap the 6 and the 4, and we would again have a permutation that has exactly 3, 6, and 9 as the pinnacle values. If we were to swap the 6 and the 4, the 6 would be further to the right in the permutation. This notion of making sure that all the pinnacles are as far right in the permutation as possible will come up later. But for now, the important thing to know is that for a given pinnacle set, there could be many permutations that have that as the pinnacle set. So maybe you wonder, is there are sets that are not admissible? And whoops, yeah, here's a set that is not admissible. And it's interesting to think about why for a moment. The reason that you cannot have both 3 and 4 being pinnacles at the same time in a permutation is that both the 3 and the 4 need to be surrounded by smaller elements. And the only elements smaller than both 3 and 4 are 1 and 2. So effectively, we don't have enough small elements to surround both the 3 and the 4. Even if they shared an element between them, you still need 3 small elements. So 3, 4 is not admissible, and no set containing both 3 and 4 will be admissible. So since some of these sets are admissible and some are not, a reasonable thing to ask is how many of this possible subsets are admissible? Is it like half of them, or are they counted by some funny number? And thankfully, in 2017, Davis, Nelson, Peterson, and Tanner were able to show that for a given length of a permutation, there's exactly n-1 choose n-1 divided by 2 round down different admissible pinnacle sets. And this takes a long time to say. So effectively, if you have n-1 things, the number of ways of choosing just about half of them, that is the number of different admissible pinnacle sets. So the next reasonable question is that since the number of admissible pinnacle sets is counted by a binomial coefficient, is there a nice bijective proof of this result? There are proofs that aren't bijective, but we like to have the bijective ones when we can. And there is. But before we get into that, let's more carefully define what we're going to be bijecting to. I'm going to introduce this, or maybe you've seen it before, this notation where I have brackets in the binomial coefficient. The brackets to n means all the integers from 2 to n. And we are specifically choosing subsets of those integers. So whenever you see this binomial notation where I have brackets 2 comma n, this is not a number. This is the set of all subsets of the integers 2 through n containing just about half of the elements. So in the brackets, it's a set of subsets. There's no brackets, it's a number. And of course, since there are n minus 1 numbers from 2 to n, there are n minus 1 choose just about half possible subsets. Now, you may wonder, why are we doing 2 through n instead of 1 through n minus 1? And I don't really have a satisfactory answer to that. I suppose 1 is a little less interesting than n because 1 can never be a pinnacle value where n can. But essentially, you just need it to be this way for the bijection to work out. So I'm sorry if you want a better answer for why we're starting at 2, but that's why. All right, so onto this bijection. So Davis et al. Were able to find a correspondence between admissible pinnacle sets and subsets of this form, subsets of the integers 2 through n containing just about half of them. The bijection involved lattice paths. So you would take your subset and then those elements would be the down steps and you get a lattice path, and then you would label the steps, and then certain steps that had certain properties would be marked. And then the marked ones, if you took their labels, that formed an admissible pinnacle set for some reason. And you could go backwards. If you had an admissible pinnacle set, there was an algorithm you could follow that generated a lattice path. You read off the down steps, and that was your subset. So it was a bijection, and it worked, and it's nice, but it was rather lengthy to prove. And at least when I read through it the first time, it didn't really make the connection between admissible pinnacle sets and subsets very obvious, at least to me. It felt kind of roundabout. So what we wanted to do is see if we could come up with a bijection that made this connection a little bit clearer. And we were able to do that. So that's what this presentation will be. We'll be outlining the bijection we were able to find between subsets of this form and admissible pinnacle sets. So here's the overview of the bijection, and then we'll go into some details. First, every admissible, I guess I should start at the bottom because that's labeled 1. We introduced this idea of interleaved permutations. All right, and I'll tell what they are in a second, but the important thing about interleaved permutations is that it's very clear that there are n minus 1 choose just about half different interleaved permutations. Then for admissible pinnacle sets, we want to choose a particular permutation that has that pinnacle set as its pinnacle set. And we do this in a way with right canonical permutations, and I'll get into what they are later. But the important thing is that there's one right canonical permutation for every admissible pinnacle set. And then as the final step, we show that every right canonical permutation is in fact interleaved and vice versa. And then this completes the bijection because every admissible pinnacle set will have a right canonical permutation, which is also interleaved, and then all the interleaves are counted by the binomial coefficient that we want. So this is the idea, and we'll get into some details. I'll start with the interleaved permutations because they're a little bit easier. The important thing about interleaved permutations is that they are constructed based off of a subset of the integers 2 through n. Particularly a subset containing just about half of them. So we let A be this subset. And what we do is we construct a permutation by placing the elements of A in all the even indices in increasing order. And then we go and place all the elements not in A complement, in the odd indices in increasing order. So for example, suppose that A was 3, 4, 8, 9, and A bar is all the rest of the numbers. And A could be anything as long as it contained 4 numbers and did not contain the number 1. So we place the elements of A in the even positions in increasing order, and we place the rest of the elements in the odd positions in increasing order. And there's your interleaved permutation. We called it interleaved because it's essentially 2 increasing subsequences interleaved together. And hopefully it's clear that there are n minus 1 choose just about half of these because every interleaved permutation is constructed by a particular subset A. And given the interleaved permutation, we can always recover A by just reading off the elements in the even positions. So these permutations are very easy to count. Now I should make it clear before going on that we don't know anything about the pinnacle values. It might seem like the direction I'm trying to go is I'm going to say that all the red elements are the pinnacle values, but that's not actually the case. In this example, 3 is a pinnacle value, but 4 is not. And there are other examples where some of the blue elements end up being pinnacle values. So just because we constructed the interleaved permutation does not mean we have any handle on what the pinnacles are or where they appear. These are simply permutations that are easy to count. All right, let's put that on the back burner for a second. We actually want to bring pinnacles into this somehow. So now we have to talk about right canonical permutations. And before I get into the definition, the concept behind these is much easier to understand than the definition makes it sound like. Essentially, we're given a pinnacle set, and we want to come up with a permutation that has that pinnacle set. But we don't want just any permutation, we want a canonical one. So we choose the permutation in which the pinnacles are as far to the right as possible. And that's the right canonical permutation for that pinnacle set. So more specifically, how do we construct this thing? Well, suppose someone hands you a pinnacle set, an admissible one, and we're going to order the pinnacles from the smallest to largest. And we're going to let S bar be all the rest of the elements we don't want to be pinnacles. And then we have this algorithm for when n is odd. There's another one for when n is even. It's pretty similar, so I'm not going to include it. But for n odd, this is what you do. We're going to build our permutation from the end forwards, from back to front. And we're going to start by placing the non-pinnacles, starting with the largest, the next largest. And we place non-pinnacles at the end of pi until the first time we place something smaller than the largest pinnacle. And then at that moment, we place the largest pinnacle in the next position. Then we go back to the first step and we place non-pinnacles in decreasing order until we place one smaller than the next largest pinnacle. And then we leave that pinnacle. And we keep doing this until all the elements are placed. Again, this makes it look more complicated than it is. So let's do an example. So suppose someone hands us this pinnacle set, 3, 8, 9, which is admissible. And they want us to construct a right canonical permutation. Well, if we follow the steps, the first thing we do is we place non-pinnacles at the end of the permutation. So we place a 7. And we look, and 7 is smaller than 9, so we stop, and we place a 9. Now we go back to the first step, which is we continue placing non-pinnacles until we place something smaller than the next pinnacle value, which is 8. We don't have to go too far. We place a 6, and 6 is already smaller than 8, so we're done with step 1. We go back to step 2 again, and we place the next smallest pinnacle. And so far, this seems to be doing pretty good. 9 is already a pinnacle value. 8 is on its way to becoming a pinnacle value. So this seems to be giving us the pinnacle values we want. We go back to the first step. We lay some more non-pinnacles. So we put down 5, but 5 is bigger than 3. So we can't put down 3 yet. If we do, 3 will fail to be a pinnacle. So we have to put down another non-pinnacle, and it's still too big. We put down another non-pinnacle, and there we go. That's smaller than 3. So now we can place 3 in the next slot, and we finish off by placing the 1. And the resulting permutation has pinnacles 3, 8, 9, just like we wanted, and no others. And furthermore, all the pinnacles are as far right as possible. Now technically, you need to prove this process always works, that it terminates, that it always gives you a permutation with the desired pinnacles, but that's not too hard to do. You basically trace through the algorithm and make sure it does what it says it does. And maybe, some of you are already thinking about why this is true. The important thing about right canonical permutations is that given any pinnacle set that's admissible, we can always construct a unique right canonical permutation for it. And similarly, any right canonical permutation, you read off the pinnacle values, and that's the pinnacle set that generated it. So notice that in both the examples I did, we ended up with a permutation 1, 3, 2, 4, 5, 8, 6, 9, 7. So that permutation is both interleaved and right canonical. And in fact, we claim this always happens. Every interleaved permutation will turn out to be right canonical. It will be generated by some pinnacle set. And every right canonical permutation will turn out to be interleaved. The proof for this, I'm not going to show you guys because it's not very interesting. It's mostly just case checking where you take elements, compare them to the elements on either side or maybe 2 away. But the point is you can do it. It's not that hard and it's relatively short proof. So proving interleaved permutations are the same as right canonical permutations gives us the bijection. If you have a subset, you take that subset, you construct an interleaved permutation, and then you read off the pinnacle values that appear. If you want to go the other way, you can start with a pinnacle set, you construct its right canonical permutation, you reinterpret that as an interleaved, and you read off the elements in the even positions, and that gives you your subset. So this is the bijection we wanted, and I feel like this makes the connection relatively clear between subsets of the numbers 2 through n and admissible pinnacle sets. Now, a reasonable thing to ask is that we have this bijection, and there already was a bijection out there for lattice paths. So are the bijections like related somehow, or are they completely different? And it turns out that they're actually exactly the same bijection with different paint. We did not know this until after we proved the bijection, but it turns out that in both cases, if you start with the same subset and then go through all this stuff, the pinnacle values you end up with the end are going to be exactly the same pinnacle values. So same input means same output in both bijections. So you can take whichever one you prefer, the one that uses interleave permutations or the one that uses lattice paths, whichever you find easier to understand. And that's all I have to present to you all. So I want to thank you all so much for coming. And if you're interested in seeing the original bijection that used lattice paths, here's a link to the paper. They did a lot of interesting work, not just the bijection, but some other things with pinnacle sets. So it's a fun read. That's all I had to present. Thank you again for coming. I really appreciate it.
Thank you, Quinn. Are there any questions at this time?
So can you also do a left canonical permutation for a pinnacle set?
Yes, you can. And in fact, that's like the easiest sort of permutation to generate. If you gave me a pinnacle set, it's most likely to work out if you start from the left. And that's what the Davis, Nelson, Peterson, and Tenner did in their paper. But unfortunately, if you construct them from the left, it's not so clear how to relate those to subsets. So that's why we had to do from the right.
Is it just taking the permutation that you obtain from the right canonical permutation that you obtain and just reversing it? Or is it not?
You can't always reverse it. What was done in the paper was you would start by placing 1 and then the smallest pinnacle value, and then the smallest non-pinnacle, then the smallest pinnacle, and then you would alternate until you ran out of pinnacles, and then you just place the rest of the non-pinnacles. So in both cases, you started with 1, but the pinnacle values in that case would be to the left instead of to the right. Yeah, thank you for the question.
Hi, I had a question. Is there some easy to check condition if a pinnacle set is admissible? Like if you just hand me a pinnacle set, like can you tell me immediately whether it's admissible or not?
Yeah, that's a great question. I believe, does this work? It was recursive. Like you would order the pinnacles from smallest to largest, and you would take, the first so many, and I believe that they had to be, I don't remember off the top of my head, unfortunately. It is a good question.
Okay, but if it's recursive in some way, then it's probably just like do exactly your right pinnacle construction and see if it works. If it works, it's admissible, and if it doesn't, it doesn't, right?
Yeah, that's basically what it was. You're correct.
Okay, cool.
Yeah, good question. Thank you.
Do your pinnacle set form some kind of nice poset or under inclusion?
That, as far as I know, is still an open question. It was posed in this paper here. I don't know if they did it under inclusion or not, but they did try to make a poset, and it wasn't very clear how to construct it, at least at the time.
Okay.
Yeah, that's a really great question. Something probably people could work on if you find this sort of thing interesting. I don't know.
Yeah, I think we have to wrap it up. Thank you for all the great questions, and thank you, Quinn, for your great talk.
Thank you. I appreciate being here.